Welcome to RCast, the official podcast of the RChain Cooperative. RChain is a complete concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the director of content for RChain. We cover a range of topics on this podcast, from the foundations of blockchain in general to the specifics of RChain, including our foundational language, Golang, as well as issues in calculus, governance, security, and the forthcoming businesses and dApp development on our platform. Please check out rchain.coop to learn more about our platform, as well as information on becoming a co-op member.
So I want to have a little bit more technical deep dive in this conversation about the proof theory stuff that I talked about. The last time we talked about it, I gave a sketch of the intuitions, and I wanted to present what it looks like if you have a minimal theory. I'm gonna screen share so we can talk, and then I'll make this draft available for people to look at who are listening to the podcast later. So basically, the idea is that we're gonna take in Levere theory, a graph-enriched Levere theory, and we're gonna produce a new graph-enriched Levere theory in stages. So this graph-enriched Levere theory represents an encoding of a notion of computation. So effectively, it's a rewrite system. The constructors of the theory are going to be your term constructors, and then we're going to have some rewrite rules. Now, the way we're doing graph enrichment is a little bit different than the way Christian and John Buys have done graph enrichment. So we actually add the theory of graphs on top. What that does is it gives us a way of talking about source and target, which is a little bit closer to the standard SOS semantics. So it's just a notational convenience from my perspective. Maybe there are other technical details that we might talk about, but let's just take a look at what a minimal such would look like. So we have one non-trivial generator constant. Since our rewrite rules are interactive, we have to have at least one term constructor that takes two arguments. That's what it means to be interactive. The left-hand side of our single rewrite rule is going to take a constructor and two arguments and then produce a new term. So there's one constant C, and then there's a binary term constructor K, and then there are left and right identities for K. Now those might not always exist, or they might coincide. So in the case of lambda, you have a left identity, but you don't have a right identity.
Yeah.
In the case of pi or rho, you have both identities, but they coincide because the term constructor K, which is par in that instance, is commutative.
Yeah.
That makes sense.
Cool. And so then the source of your rewrite rule rho must be K of TU. And then the target is just going to be some function of T and U, right? It computes a new term based on the information from T and U.
So yeah, I was a little confused, like why rho is a rewrite rule, because right now, just writing it out, it looks like another operation.
It's the source and target part of it that give it the rewrite rule semantics.
Yeah, because y'all are treating everything as an edge, so you can talk about
exactly.
Source and target.
Yeah, exactly.
Okay.
So now we're going to take one step. We're going to get to our goal in two steps.
Oh, can I ask a question before we move on?
Yeah, sure. Go ahead.
So with the that target equation, you're saying the target of that rewrite is like f of t and u. What's the f all about?
It's some way of calculating a new term from the information given in t and u.
Okay, yeah, that's cool.
For example, in the case of lambda, t is going to be the abstraction. Say lambda x gives you m, and n is going to give you is the argument to the abstraction. That's u. And then when you calculate f of tu, what you're going to get is m, where you substitute in for x everywhere.
Right. Okay. Yeah, I'm on board.
So now we're going to modify this by introducing an evaluation context. Now you could do this in one of two ways. You can make R, which is our evaluation context, R standing for resource, take a term and produce a term, Or you can make R be a constant, and then you supply it to one side of K.
Yeah.
Either one of those is workable, at least in the theories that we've looked at. Mike prefers this presentation, I think, because of the sort of what happens with lambda. You can do it either way. And then we're going to add two more operations. And this corresponds to the fact that if I jump to the rewrite rule first, then I can explain the other term constructors. So now we're changing the source of the rewrite rule. So the only time you get to rewrite is if you have R of K of TU. If you don't have that R, K just sits there. It doesn't evaluate.
Yeah.
Since we've modified it in that way, K becomes a pairing operator of some kind. It's effectively a kind of tensor because you don't necessarily have a way of getting anything out. And you can think about this in terms of computational reflection. In the old theory, KTU provided all the information you needed to do a computational step. And now what we're saying is you have to have this additional piece, which is R, but there's no structure to R, right? So R is just a gating thing, like adding flow to a computational step in the row line. That's the basic intuition. So you could think of it, denying R is now making K reflective. So that reifies your K now reifies your computation. And what you'd like to do is to extract the information stored in the reified computation. And we provide two extractors. One, which we call par, and that, again, takes two terms and gives you a term. And the other, which we call cup. And par basically does, when we reassemble things, it's going to reassemble them or wire them up in parallel. And cup will wire them up in series.
Just to be clear, so you're saying that by denying the resource to the original computation or rewrite, or however you want to say that, you're effectively turning it into data, which you can then put into other computations or something along those lines, right?
That's exactly it, yes.
Yeah, cool, okay.
So now we're going to take our third and final step, which is to add one more sort. So this is the final expansion of the original theory. So this extra sort represents the notion of a context. When our term data type is a differentiable functor, then this sort corresponds to delta of t.
Yeah.
Okay. That's like the Connor McBride's zipper stuff. I don't remember exactly.
That's exactly it. That's
cool.
Connor McBride stuff.
Yeah.
So that means we're going to add another constant, which is whole. Yeah. Which goes from 1 to the context type, and then we have left and right introductions. So you can put a context in the left side of K, and a term in the right side, and now you get a new context.
Yeah.
Or you can put a context in the right side of K and a term in the left, and now you get a new context. We're going to distinguish when a context is applicable, meaning that when we can actually do a substitution for the whole. So we're going to write that with left and right bangs, depending on whether the whole is in the left side or the right side.
This is like abstraction, right?
This is like abstraction, except that we only ever have one whole.
Yeah. Okay.
So it's like even more restricted than linear abstraction.
Okay. Yeah. So you got the left and the right abstraction, basically, right?
Yeah, exactly. That's right.
Cool.
And then we have a notion of substitution. So if I have a context, I turn the whole and get back a term. And then everything else remains the same, but we have some identities. So when I apply an at to a banged whole and a t, I get back t. And then when I apply an at to banged context, I distribute the at inside.
Mm-hmm.
So those are the extra equations that we add to this theory.
Do you need any equations for par and cup to describe how they work?
No, we don't, actually. The cut will determine all of that.
Okay. Yeah.
Cool.
So now I can define a notion of arrow. So this is prefacing what's to come. because these are expressed in terms of tals, which are types. Effectively, an arrow is going to be the collection of contexts chi, such that I can find some t that allows me to decompose the context so that t fills one side and there's a hole in the other. For any u in tau, when I apply u to that chi, if there is such a rewrite to v, that v is in tau prime.
Yeah.
And we can do this on the left and the right.
Is this arrow, I think it's guarantee and
It's rely guarantee. Yeah, that's exactly what it is. This is a rely guarantee arrow. There's an ISO from this definition to Kai Race's definition. He doesn't use context, right?
Right, yeah, but it looked really similar and reminded me of that.
That's exactly what it is. So it's a rely guarantee notion.
Okay.
So now we can form these types, right? So we start with a top, which is going to denote all terms. And then we have, if you have, a tau and a tau prime, you can form the arrows in either direction. All C's are now lifted up to be types. Since these taus denote sets, we also have the empty tau, so that's a constant. And that's going to correspond to the absurdum in certain cases. You can also take taus and union them together. You can apply an R to a tau, so it's a tau which you've now resourced. You can make Ks of taus. And then we have all the linear types. So now we have the row tensor, which takes 2 taus, and that's basically going to be a K without a resource, but it's cuttable, right? So it's indicating which way you're going to wire things up when you cut, right? So K without the indication, you don't know how to wire it up. The same with pars and caps are like the tensor, but it's an indication that it's a K that you're going to unpack with a cup in series. And then we have some abbreviations. So we actually have lots of negations, right? Depends on what you put in the right-hand side or it depends on what you put at the point end of the arrow. So if you put the identity at the pointy end, the right identity at the pointy end, that's like linear, the perp operator, linear negation. If you put the empty set at the pointy end, that's like classical negation. And then you have left and right versions of those.
Can I ask a question about the types?
Yeah, sure.
You have something like the empty set, right? Because you said the taus were basically sets. So this is like a realizability thing, right?
That's exactly the interpretation is realizability.
That empty type, is it different from bottom or is it the same thing?
It functions much the same way that bottom does, yes.
Okay, cool.
So now we can go on to our proof rules. I've color coded it. So if you follow the red side, you're building terms. If you follow the blue side, you're making proofs. And when you have both sides together, you're typing your terms.
Very nice.
And when you type your terms, you can view it as constructing a type for your term, but you can also view it as extracting a term from a proof. So it works both ways. And that goes back to this whole point about correct by construction. At the end of the day, correct by construction is all about extracting programs from the proofs of their correctness. That's the idea.
Yeah.
Okay.
That's cool.
So I'm going to read turnstile as thinks that. So we're gonna build proofs in terms of sequence. We have both intuitionistic versions of these sequent calculi, and we have classical versions. In the intuitionistic version, the left-hand side of the turnstile is some typing context, which can have commas in it, which is just interpreted as a list of assumptions. And the right-hand side has exactly one thing on it, one typing assignment on the right-hand side. So if we use gamma and delta to range over the typing context, then gamma turnstile t colon tau is read. Gamma thinks that t is typed tau. So that's how we're building these rules. And so our ground of this is that we have the empty typing context to derive that a term C is of type C. Since every constant gets its own singleton type, that's essentially recording that decision. And that's how the whole system gets off the ground. Well, no, there's one other way it gets off the ground, which is the axiom rule, which I'll talk about in a little bit. So then tensoring just says if gamma thinks that t is of type tau, and delta thinks that u is of type tau prime, then if you take gamma together with delta, so you have both typing contexts, then you get that k of tu is of type rho tau tensor tau prime. If you have a single typing context gamma that thinks that t is of type tau and u is of type tau prime, then gamma thinks that par of tu is of type rho par tau tau prime. You can kind of see the pattern.
So that next cut tells you why you needed them to be in the same context?
Yeah, that's exactly right. So now, when we do a cut, so we have a cut rule now, we only ever cut pars against tensors and cups with caps and things like that. So if I have a par and a tensor, which is just a k, right? It's a k that's been denied a resource. When I cut them, I'm going to supply a resource, which will allow it to evolve. Inside the R context, I have the capability to evolve, but I'm not going to show all that evolution in the type. I'm only going to show the result, which is RK, which is the right-hand identity.
Why RK?
Because if you actually run this through the arrow definitions, you'll see that that's exactly what you get.
Oh, yeah, no, I just wanted to speculate as to why it should be the RK.
Yeah, go for it.
Is it because we're looking at the rho par of the tau perp and tau prime perp, and we're
Exactly.
yeah,
Exactly what's going on.
yeah, okay.
Yep. So tau perp eat up taus.
Yeah, cool. Yeah, I definitely did not see that the first time I looked at it, but hearing you explain it again, it made a lot more sense.
No, that's exactly what's going on. So basically, this is like a generalized categorical composition, right? This is eating, like when you have an A to a B and a B to a C, the B is occurring in opposite polarities. So when you plug them together, the B gets traced out.
Mm-hmm.
Right? So this is a generalized version of that tracing out.
Cool.
But in the formation of the par, like you didn't require. Oh, I see. Okay.
Yep.
The duality is happening across the par and the parallel.
Yeah, exactly.
Yeah.
And notice what we mean by parallel, right? So the T prime goes with the P and the U prime goes with the U. Now we'll see the in series version. I serialize, and here I'm insisting on a single gamma. We could do a version of gamma with a delta. I'm still sort of debating on which one is better. It's probably better to separate it out into a delta thinks that U is of type tau prime. But anyway, so the point is that you're declaring an intention, right? You form a K. This sort of gets in the way of principal typing, because this is, when a programmer gives this information that is typed rho cap, then they're saying, I intend for this to be used in a serial way as opposed to a parallel way.
So you just get to choose which one?
Yeah, you choose. The programmer is indicating this is how I want to use it.
Huh.
It's a type annotation.
Yeah.
Yeah, so I just wanted to ask if that corresponds to that newer syntax for rolling, where we have, obviously we still have, the parallel composition, but then we also had sequential composition. Does this have anything to do with that?
Obliquely.
Okay.
It's not. It's in the same vicinity, but it's for a different purpose.
Yeah. Okay, understood.
In the same way that we can pack up T and U into a K, we can set up for unpacking, which is we package up a T and a U in a cup, and then we know that when you've got a T and a U packaged up in a cup, when you cut it together with a cap, they'll be extracted. And so this is exactly the same kind of thing, but notice that our types are more sophisticated now. we now have to use the arrow to get the sequencing exactly right. So in the serialized, deserialized cut, we're insisting that T is of type tau double prime arrow tau perp, and U is of type tau prime, and that tau double prime, right? And I think, did I get that? I think I need an extra perp in there somewhere. But then we also have tau prime arrow tau in the left-hand side, so that T prime is tau prime arrow tau. And then we have a tau. Oh no, I've got it right. I've got it exactly right. So what's going to happen is we're going to run KTU, so that tau double prime is going to be supplied to the arrow, which is going to give us the tau perp. And then the tau prime is going to be supplied to the tau prime arrow tau. And so,
okay.
right. So it's going to run to a tau perp and a tau, and then those two are going to run together, and we get what we want.
Mm-hmm.
Okay. Yeah, that makes sense.
So arrow basically allows us to do sequentialization.
And the perp was what again?
The perp is just an abbreviation, right? It's a form of arrow.
Okay.
So you see, when you stack these, what we're really doing is the double negation translation.
Why is it going to be sufficient to focus on these dual types, or like these types that are going to annihilate each other?
So basically what this gives us is the session type capability. So this whole thing is now showing that we have both the original sort of model theory capabilities, so the chi-race capability, together with the session type capability. So we're marrying the two together. These proof rules are all about the session type stuff. And then the model theory gives you the rest of the chi-race semantics.
Can you say a little bit more about the session types and kind of how you're thinking here? I don't know a whole lot about session types. That's why I'm asking.
Session types have largely been viewed from the perspective of linear logic. Like Wadler's paper, Sessions as Types, I think is what it's called.
I mean, it's about like resources that are available on specific channels or something.
Yeah, basically, it's thinking of a session as occurring over some group of channels. Really, is what it comes down to. And it's reminiscent of the kind of thing that you see, a generalized version of what you see when, for example, a program opens a session to a database.
Okay.
And you know that has a very particular shape, right? The shape is open session, do a bunch of reads and writes, close session. Right?
Yeah.
So session types generalize what you can do with that.
Okay.
Yeah. And this goes further. It goes past that. So what we're doing is finding, in many ways. I mean, like no, I'm not dissing Phil here, but in many ways, Wadler's semantics are very dissatisfying because tensor means sequential composition.
Okay.
So it's not, in at least in his original 2012 paper, but this recovers where the parallel is and where the serialization is. So we're showing both capabilities here. We can see that cut is just a special case of either the par or the serialization. So just the ordinary cut of, a tau with a tau prime, a T prime with a tau perp and a T with a tau. That's really just a special case of the other. You can build this notion of linear cut from that.
Yeah.
Okay. So you're saying that's where the cut elimination comes from?
Right. Exactly.
Okay.
Yeah.
Okay.
Exactly. So the more general thing is, and it's really obvious, but any proof that uses a cut can be turned into a proof that doesn't use a cut. And the way you do that is wherever you've got a cut, you just replace it with the right-hand side of the rewrite rule.
Okay.
Yeah.
Yeah, that makes sense.
Yeah. So now proof normalization is exactly the same as running your program. So we've got the tightest possible Curry-Howard correspondence you can have.
Yeah. Cool.
We have a notion of axiom, and this builds upon the notion of context, right? So, if you type whole as tau in your typing context, right, then you get that whole is of type tau in the consequent, the right-hand side of the turnstile. So that's axiom. And then we can do left and right cut. So we can form lambdas by discharging our whole obligation, saying that, hey, you really need to apply this to something. Right, so if I have gamma together with whole is typed tau, thinks that u is typed tau prime, then gamma thinks that u bang is typed tau prime, on the pointy arrow of a left pointing arrow tau. I said that really, I butchered that. It's easier to say from the other side. So if gamma together with whole is type tau, then think that t is of type tau prime, then gamma thinks that bang t is of type tau arrow tau prime. So if you give me a tau, I'll give you a tau prime. Is basically what both of these rules are saying.
This is saying the whole is of type tau. Does the whole have a determined unique type, or could it be of multiple types?
If you declare that the whole is of type tau, you're saying, or you can prove that the whole is of type tau. Either way.
Okay, but we can make contexts have wholes of any type.
That's what the axiom rule says.
Okay, cool.
So is typing the whole just kind of saying like that context is expecting a certain type?
Yeah, it's just like a simply typed lambda calculus. Think of the whole as a variable. We're just saying that the variable is of a particular type.
Yeah, okay.
So now we can have a context cuts, and we can cut on the left or the right. Well, let me do the right one. It looks like I've got another orphan situation. We're going to fix that up. So the right one is, if gamma thinks that bang t is of type tau arrow tau prime, and delta thinks that u is of type tau prime. Oh, did I get that wrong? I did. Yeah. Sorry, that's a typo. Delta thinks that u is of type tau. Then gamma together with delta thinks that r ktu is of type r tau prime. So it does exactly what you expect. It's like it's recording the type that's at the end of having done the rewrite, right? So you can't see the rewrite stuff happening inside. Does that make sense?
Yeah. Okay. So you just see the resulting type, I guess.
Yeah, that's exactly right. But the term is ready for rewrite. It's a k of a tu supplied with an r.
Yeah. Right.
There's not a lot of surprises. It's just that now we're going to have only one-sided sequence. So everything is pushed to the right of the turnstile, and we do everything in terms of the perp operator. Now, in truth, we should have not only an axiom with the perp on the right, but we should also have one with the perp on the left, but I haven't put those rules in. And then everything else just kind of follows. And the real difference is whether or not your system admits only double perp close things, in which case you have a classical gadget, or if your system doesn't enjoy double perp closedness, in which case you have the intuitionistic setting. So for example, lambda, doesn't enjoy double perp closedness. You can find a subset inside lambda that does, but lambda itself, it doesn't obey the law of the excluded middle. So you would use the intuitionistic version.
Were those two deductions above the only way to form something of type tau triangle, tau prime?
Those are the only ones you got.
And you can get everything that way?
I think so, yeah, but we'll shake out in the proof.
Huh, okay.
I have an intuition for what you mean by double perp closed things, but I guess my intuition is coming from thinking about vector spaces and inner products, and it's probably not the right way to be thinking about it.
That's a really good way. It's really important to test both from that perspective as well as from the sort of the programming language perspective. By double perp closed, we mean that if you take the perp of the perp, you get back to where you started.
Oh, okay, yeah, that's what I thought, and it also looked like you had some notion of like the polar. And that looked like the other notation that you defined. I forget what it was at this point. But it's like the degree symbol or whatever you want to call it.
Yeah. If you think about it topologically, right, and you interpret perping or negation or whatever as closure. So if I have some topological space and then I take the closure of it, and then I take the closure of it again. So the second time it doesn't move, right, because it's already closed. But that first time I may have included more points. So for example, if I take a unit interval without the endpoints, and now I take the closure, then I'm adding the endpoints. And then when I take the closure again, I won't add any new points, so it's the same space. But that first time I did add the endpoints, and so the double perping it doesn't get me to the original space. So that's one piece of intuition. If you've got double perp closedness, so or some kind of involutive operation, then then you can use the classical piece of this, but otherwise you're going to use the intuitionistic piece. Christian, to your thing, notice that U is some complicated, it's potentially some complicated context. U is going to have a hole in it, right? Right.
Wait, why?
U is not a hole, right? It's a term, or it's a context. Right.
All of this is context?
Yeah, exactly. That's yeah. So I start from a hole, and then I can build Ks with holes and all kinds of stuff, right? So in particular, I can start with 2 holes, and I can make a K with 2 holes out of that, right? And then I can fill one of the holes, and I can abstract over the other one, and so that's how you get all of the richness. Basically, U has some hole buried deep down inside it, and the typing context is recording the fact that you're going to have to discharge that at some point.
Yeah, I feel like at the beginning you were describing how to inductively build up context as terms, but I don't remember seeing earlier like how you build up all contexts with their corresponding typing judgments.
That's what this is. That's what this is doing.
I mean, right now you're not including any of the constructors. Like
that's up here. All of these rules apply down here.
Okay.
Yeah, that's the idea.
They just also have a hole in them.
Yeah, exactly.
Okay.
Oh, I just wanted to say that I'm really glad that you explicitly said that U has a hole in it, because I was not thinking about it as a context. So I think this makes a lot more sense now.
Cool. Yeah, I should probably use Kai's instead of U's.
It might be helpful.
Yeah, good idea. Thank you. That's great feedback. That's great. So that's pretty much it. I mean, there's, obviously a lot more details, by the time it's all done. But I mean, what I can say is I'm now confident enough in the whole construction that I'm going to do an implementation in Agda. I'll probably do it over the Christmas holidays.
Great.
Yeah. So it should be a ton of fun. And then, as we mentioned before, we introduced this R sort of out of thin air, right? And if you want, you can kind of split your original theory into a red version and a black version. For one of the theories, the R can be the other color, and vice versa. You don't have to cons up an R out of thin air. And also, you can generalize your context to give you richer nominal phenomena, and then you can make all of those names arise from quotations of your original theory. And then what remains is, either to take the, Fiore et al. Approach with the higher order abstract syntax to do the nominal stuff, or to use the Clausen approach with the nominal Labir theories. And then we're done. We've got all of the juicy bits of lambda and pi accounted for, and other things. Now, the one thing I'm interested is to run this on the ambient calculus, which is not a substitution-based calculus, and see what kind of logic I get. But, there's the algorithm.
Cool. You said that the ambient calculus is not a substitution-based calculus, and I knew that, but it's been a while since I've looked at ambient calculus. So what is the notion of reduction in ambient calculus?
It's whole tree rewrite.
Oh, that's right. Okay.
Yeah. When an in hits a term, it'll move into the ambient. When an out hits an ambient, it'll move out of the ambient. Right. So it's actually literally, it's reconfiguring the whole tree. That's why it's not so good for internet stuff, because you're effectively reconfiguring the whole internet. It's not local. Right?
Yeah, that sounds expensive.
Yeah, and even though the rewrite rules are local, the effect of the rewrite rules is global. Pi and rho and things like that are much better because it's really a local exchange, whereas ambient stuff is not a local exchange.
Okay, cool. Yeah, that's a great point.
I've given lots and lots of talks where I kind of go through the different calculi and I say, well, this one isn't so good for this reason, and this one isn't so good for that reason. But I've never sort of written it up and made it like really crystal clear for people to understand like why the join calculus doesn't work for programming the internet.
Yeah, I think that would be super interesting if you're willing to do that.
Yeah, it's yeah.
Maybe it's a low priority item at this point.
It's a kind of low priority for me, but
yeah,
I'd love to get someone to collaborate with me on it.
In this paper, you're describing like a class of enriched Levier theories that you consider some sort of theories of interaction.
Yeah, that's right.
And then you're like describing this construction you can do on all of them to augment them and equip them with resources and contexts and these useful types.
Yes.
And you're going to be proving nice things about that.
That's exactly right. So in terms of the format of the paper that we hope to get out in the not too distant future, after presenting just sort of the minimal theory, then we'll apply it to lambda and rho. Depends on whether or not we go all the way to nominality, right? We might just apply it to SKI and the rho combinators. The nice thing about the rho combinators is I don't have to deal with nominality, and I don't have to have some exogenous supply of names. That shows the theory in action applied to a particular, pair of rewrite systems that have nice properties. And then we do the proofs of the cut elimination, all the good Curry-Howard stuff, and then show a few properties, right? So like in the ETAPS, the 2005 namespace logic paper, one of the cool things about the paper was all the properties that I listed that, were just like, I literally just came up with them off the top of my head. Well, here's a cool one. We can do a firewall. And, here's a cool one. I can encode XML schema. And, just illustrating that there's some really fun properties here, like deadlock freedom, for example, or non-leakage of information from a higher security context to a lower one. Those are properties that we can pretty easily write down in the corresponding type system. I think that should be more than enough, right? So you've got a fairly broadly applicable algorithm. The output of the algorithm includes a type system that can say really interesting properties, and the corresponding system has cut elimination, proof normalization properties. So I think that's enough, goodies to constitute a decent paper.
So do you know of any influence that like confluence of the rewrite system would have on the type system that's being built?
Yeah, it'll make it much more likely to have principal types.
Okay.
One other thing about the types, in the first half you were talking about an enriched Levier theory, and then in the second half you were talking about a certain type system. But where exactly is that type system happening? Are you talking about it purely syntactically, or are you going to try to fit it into the Levier theory framework?
So what you're asking is, what's the ontological status of the type system?
Yeah.
Right. So to be perfectly honest, I think we get another category, and the types should be the object of that category. So the Levier theory is happening in one category, and the type system is happening in another category.
Mm-hmm.
And so what we should do is to see that category, and then we see the morphisms are the proofs in that category. So if we've done it right, then there'll be a relationship between that category and the category, where the Levier theory arose, right? So there'll be some functor between the two.